It's costing the global economy trillions of dollars to go down the net zero route. There's no measurable benefit from it at all. We really should be spending our money, perhaps better preparing ourselves for what Mother Nature is going to throw at us. Spending all the money on the temperature control knob, which doesn't work, doesn't seem to me a very sensible thing to be doing.
This is Climate Debrief, brought to you by the CO2 Coalition. I'm Angela Wheeler. Today we'll be discussing the greenhouse effect with CO2 Coalition member Rob Louw. Rob Louw is a global leader in chemical engineering and an advocate for environmental truth. With a Bachelor of Science and Master of Science from the University of Cape Town in South Africa, Rob's career spans the petrochemical, synthetic fiber, and titanium dioxide industries. Rob, it's so nice having you on Climate Debrief.
Thank you. Pleasure.
Rob, in your presentation, entitled quite succinctly, The Greenhouse Effect, you begin with a quote from Albert Einstein at his 1933 Herbert Spencer lecture at Oxford. I won't attempt to say it in German, but Einstein is stating that everything should be made as simple as possible, but not simpler. How does Einstein's principle of simplicity help clarify that the greenhouse effect should not be oversimplified to blame CO2 as a dangerous greenhouse gas?
The problem is that it's a very complex science. And unfortunately, particularly for junior education, it's been grossly oversimplified. And yes, carbon dioxide is a greenhouse gas, but it is no longer a warming threat to the planet. But that fact is completely and conveniently overlooked. Typically, it is described as a blanket encompassing the Earth, and the more you add to this blanket, the warmer things are going to get. Nothing could be further from the truth. And I think that Einstein has said, please keep things as simple as possible. I fully support that. But don't go too far and make it too simple so that people get the wrong impression. And that's what we've got to guard against.
In what ways does labeling CO2 as the gas of life emphasize its essential role in biology, countering the narrative that it is a pollutant?
It's quite bizarre that it's named a pollutant. Pollutants are generally toxic compounds, and carbon dioxide certainly isn't toxic, certainly at atmospheric conditions. And dare I say, at much higher concentrations, if you go up into the space station or if you go down into a nuclear sub, you'll find carbon dioxide concentrations of 5 to 10,000 parts per million, whereas in fact on the surface of the Earth, it's only about 425 or 430 parts per million. The other reason it's not a pollutant, it's clearly an essential ingredient for plant growth. It's the most important ingredient for plant growth. Without plants, we humans wouldn't be here, because whether we eat plants or not, we eat animals that eat the plants. So whatever it is, it's absolutely vital for life, and it's been around for a very long time.
Rob, in this graph, it's quite interesting. With the net zero hysteria, many people think that carbon dioxide is the most abundant and most potent greenhouse gas in our atmosphere. But that's not so, according to your graph. Could you explain this in some detail?
If you look at the graph I've shown there, this is a breakdown of moist air, and I've assumed an air composition with 2% moisture. The problem with moist air is that it varies enormously around the planet. For example, there's virtually no moisture at the poles, but it's almost saturated at the equator. But on average, one could call it 2%. Now, if you compare that to, and the potency of water vapor just as a greenhouse gas, if you discount the effect of clouds, is a good 3 times as much as carbon dioxide, which only makes up 0.043% of the atmosphere. If you then add in the clouds to the equation, then water vapor clouds together are responsible for at least 90% of the greenhouse effect. So they are by far the dominant factor, yet water is not defined as a pollutant.
You're saying that water vapor is by far the most significant greenhouse gas, and carbon dioxide is only a very small fraction of atmospheric greenhouse gas. Is that correct?
Yes, yes.
So let's see here. Continuing your presentation, you state something very significant that I doubt many people understand. Given the temperature inversion in the stratosphere, how does this profile support the idea that greenhouse gases like CO2 have limited impact at higher altitudes?
It's a complex question, and the answer is not 100% straightforward. If you look at the radiation profile of carbon dioxide, it has an ability to emit infrared radiation both in the troposphere and the stratosphere. Now, in the troposphere, you have a negative temperature gradient. In other words, as you go higher up in the troposphere, temperatures drop. So if you increase the concentration of carbon dioxide, the emission height, the height at which concentrations drop low enough so radiation can escape to space, move upwards into a lower temperature layer of the air. And the lower the temperature, the lower the radiation intensity. In other words, the weaker it becomes as a radiator, and it means that the Earth has to warm up to compensate for that slowing down of heat escaping to the space. Now, when you get to the troposphere, you get the opposite happening. The air warms, the temperature increases, and that's because of the ozone layer up there. And what that means is that as carbon dioxide concentrations rise and the emission height rises, the emission altitude rises to a warmer temperature region, which is more efficient at radiating than it is at a lower temperature region. So it's a complex battle between the two regimes, the bit that's escaping in the troposphere and the bit that's escaping in the stratosphere. But on balance, the effect as carbon dioxide increases above the current level is very, very limited. It decreases to the base log 2. So it's done all its hard work already. It did so even long before it got to 420 parts per million.
In your presentation, it shows Earth's radiation balance. How does the equality of incoming and outgoing radiation illustrate that small changes such as from CO2 won't drastically alter Earth's temperature?
The basic principle is, it's a thermodynamic principle, that all the heat that is radiated to Earth must be radiated back to space. If that weren't the case, if, for example, the Earth were accumulating or losing some of its heat, then its temperature would continuously rise or continuously fall, and probably quite quickly. So it would make life very, very difficult because you get wildly fluctuating temperatures. The balance is maintained no matter what. The Earth is at all times balancing what comes in with what goes out. And one of the ways in which it can do that is by altering the surface temperature. If, for example, greenhouse gases were to block some of the heat escaping to space, then the temperature of the Earth would have to go up to compensate for it, so that the incoming energy balances the outgoing energy. But conversely, if the incoming energy were to reduce, then the Earth's surface would need to reduce in temperature in order to match the two. But it's a scientific or a thermodynamic fact that the heat being radiated to the Earth equals the heat that's radiated back from the Earth.
Rob, let's switch to the topic of saturation. Your presentation states that at approximately 430 parts per million of atmospheric CO2, most of the heat absorption is already complete. Can you please explain this?
Well, as the concentration of carbon dioxide increases, so the ability for it to increase the radiative forcing, as we call it in physics, reduces. And as I mentioned earlier on, it's a log2 relationship. And this is just an analogy. If you take a wooden barn, and you give it one coat of red paint, it'll look a pretty decent red color. However, if you put on a second coat of red paint, it looks a tiny bit redder, but only a small amount. But when you come to put 3, 4, 5, or 6 coats of paint on, the color doesn't change anymore. And a similar thing is happening with radiation. What carbon dioxide is doing at very low concentrations, it has a noticeable effect, like the first coat of paint does on a barn. But as soon as you get to the second, third, and fourth coat, the effect diminishes very, very, very quickly. And if you take the 400 parts per million, which is more or less where we are today, and you double the carbon dioxide concentration to 800 parts per million, you would only cause a radiative forcing of 3 watts per square meter, and that gives you a temperature rise of about 0.7 to 0.8 degrees centigrade to compensate. So that's what we're trying to illustrate here. This is perhaps one of an example of simplifying things as per Einstein for the non-technical viewer.
So what you're saying is that using the red barn paint analogy, just as extra paint coats cause negligible redness, in the case of atmospheric CO2, there's negligible warming. Is that what you're saying?
That's absolutely correct, yes.
Rob, now I'd like to discuss this chart with you. It shows global warming for each additional 50 parts per million by volume of CO2. It's very important that people understand this. Please give some details.
Okay. This adds a little bit to what I've just been telling you. As you can see with that graph in front of you, and I went down to 0 parts per million of carbon dioxide on the left-hand side, and I added 1 part per million. The amount of heat that would trap would be 1,000 times more than adding 1 part per million today. That just shows you how steep the curve is. What the graph there essentially shows that is as the concentration of carbon dioxide increases, so the effect on temperature decreases. And you can see if you go from where we are today, if we added 50 parts a day, we'd increase temperatures by about 0.2 degrees centigrade. But if you doubled our concentration and you went up to 800 and you doubled it again, you'd only increase temperatures by 0.1 degrees centigrade. So it shows you the diminishing return. The other thing I show on this graph is that, in fact, there is a limit to how low we can take carbon dioxide concentrations. If you go below 115, which I call the line of death, plants can no longer grow. And if plants can grow, then life as we know it wouldn't exist. The next mark there is the 280 parts per million, which is what we call pre-industrial. That's kind of when the Industrial Revolution started. And then you get to 429 parts per million, which I think is approximately what today's number is. It's very close. And as you can see, yes, there has been some warming since the pre-industrial era. But at most, carbon dioxide is only contributing 0.2 or 0.3 degrees to that. Because we're already very close to saturation. So if you go beyond where we are today, very little extra warming is going to occur because of carbon dioxide, at least.
Yes, and then circling back a bit to something that you said earlier and tying it in with this graph, you show the line of death that 150 parts per million is the line of death. Can you explain how this is tied to photosynthesis, and how does this emphasize CO2's vital role for life?
The plants need carbon dioxide to produce the sugars that they need to grow. They combine it with water, sunlight, and heat. And that's a basic chemical reaction. However, when you get below 150 parts per million of carbon dioxide in the air, there is then insufficient carbon dioxide to meet the basic needs of the plants for growth. Because every lab experiment that we've done shows a significant improvement in plant growth as you keep adding carbon dioxide into the air. So ignoring the 150 line of death where nothing will grow, if you go up to 1,000 parts per million, 800 to 1,000, you get double or treble plant productivity, provided you give the plant all the other nutrients it needs. So there's no question that carbon dioxide is good for plants. And in fact, if you look at the NASA photograph of the planet over the last 20 to 30 years, there's been something like a 20% increase in the green area of the planet, which can all be tied back to increased levels of carbon dioxide plus slightly warmer conditions and perhaps better fertilization.
Another question we asked Rob was this. Your overall conclusion using physics argues that there is diminishing warming effect from increasing CO2. Climate alarmists often say that any small amount of warming will lead to increased water vapor levels, which in turn will lead to further warming. You disagree with this. Could you please explain?
Yes, there are a number of reasons why I say that. The first and obvious one is if you go back, look at the history of the Earth right back 4 billion years, you can see that temperatures and carbon dioxide levels have varied for the last 4 billion years. And at no time in the past, even when carbon dioxide was at 10,000 parts per million, have we ever experienced a temperature runaway. And I think in some respects there's a misunderstanding what people mean. They don't really understand what positive feedback means. If we were to get a positive feedback, what that would mean is that any small amount of heating on the Earth would cause more heating. Well, of course, that would then cause more, and that would cause more, and that would cause more. And very, very quickly, the temperature of the Earth would run away, and it would not be habitable. That's clearly not the case. What does the proponents of the feedback mechanism also ignore is that it can go the other way. A positive feedback doesn't only mean warming, it can mean cooling, which would mean that any cooling event would lead to a runaway cooling of the Earth, which would be a lot more serious than a runaway heating of the Earth, because very quickly life would cease because plants can't grow in sub-zero conditions. So that's one of the reasons. There are other well-known principles. There's Le Chatelier's principle, where a system that's in equilibrium, if you disturb a system in equilibrium, it always wants to try and return to that equilibrium, which is typical of what happens in the natural world. In real life, an example of a positive feedback is what you get when you have an explosive, and we all know what happens when that gets triggered. Very quickly, the reactions run away, and you get a lot of destruction. Now, I'm a chemical engineer, and in all my career, all of the processes that we have rely on negative feedbacks. And the concept of a negative feedback, I think, is also misunderstood. All that means is that the system that you're controlling, for example, the Earth's temperature, the Earth has a desired value, call it 15.5 degrees centigrade, that it's trying to keep the Earth at. So it'll do everything in its power to bring temperatures back to that level. And most probably what is happening is that with a little bit of warming that carbon dioxide is able to produce, and maybe a bit more water vapor does get into the air, but that leads to further cloud formation, and that cloud formation changes the albedo of the Earth, which in turn cools the Earth. So you've got mechanisms that are competing with each other, and by and large, the negative feedback systems win. If they don't, we're in trouble, and we'll know about it very quickly.
There's a global effort to reach net zero, but you argue that CO2 is not the climate's temperature control knob, that it has become far too weak a greenhouse gas to have any meaningful effect. Could you explain these graphs?
If we achieved no global net zero by 2050, and I think very few people appreciate that, based on the what I've presented so far, and assuming no negative feedbacks, which in all likelihood, is not the case. The Earth's temperature would only warm by 0.07 degrees centigrade, which is barely measurable. If you consider the USA alone, and you reduce the CO2 outputs to net zero by 2050, you would only reduce at most the global temperature a saving of 0.01 degrees centigrade. And in the UK where I live, it's 0.001 degrees centigrade, which truly is undetectable. So it's costing the global economy trillions of dollars to go down the net zero route. And quite frankly, there's no measurable benefit from it at all. We really should be spending our money, perhaps better preparing ourselves for what Mother Nature is going to throw at us. But spending all the money on the temperature control knob, which doesn't work, doesn't seem to me a very sensible thing to be doing.
Rob, you mentioned that if the Earth doesn't autocorrect itself, how quickly would we know? And wouldn't we have already known about it? Wouldn't we have already seen the evidence that it's not autocorrecting?
These positive and negative feedbacks are not lying dormant on the planet. They're operating here and now. It would take less than a year for us to be burnt to a frazzle, because one orbit around the sun changes the Earth's net radiation by 60 watts per square meter, which is 20 times as much as doubling the carbon dioxide content. That happens inside the space of a year. So heaven only knows what would happen if the Earth could not regulate or could not control temperatures. It would be, I don't know, it would be a few years, maybe, if we're lucky. But it would happen in that sort of time span. It would be very quick. But it does, of course, depend on the strength of the feedbacks. But some of the ones you get bandied around, you get these climate models that show temperatures rising 3 or 4 degrees or 5 degrees centigrade. And interestingly, they can't even, if you take a climate model and you start back in 1970, the first time that we really got good quality global temperatures, and you test the climate model against the temperatures that we've measured since then and what they tell us, they're hopelessly wrong. But the scientists that have developed those models keep using them, and they forget that all that they are is a scientific tool to help them correct their thinking, which is wrong. If a model cannot predict the past, it most certainly can't predict the future. And I suspect that the reason is that they've got the feedback loops all cockeyed, but their models are so complex, you cannot go into them and see for yourself what's actually going on.
So it's safe to assume that if their models were correct, we would already have seen the drastic consequences that Earth can't self-correct.
That's exactly it, yeah. The interesting, I think there's one model that does work, and I think it's a Russian model, and they don't use the big feedbacks, but I don't know enough about the model details. It's very difficult to get the information out of anybody, what they've used in their models and exactly what their models are doing. But what to me is even more bizarre, you take 20 or 30 incorrect models and you average them, and you say, well, that's a better answer. It's like saying 2 wrongs make a right. It doesn't work like that. Well, it doesn't make any sense if you're making arbitrary tweaks just to try and force it to fit the temperature. It's got to be sound theory based, and then it's got to withstand the rigor of the scientific experiment.
Rob, you've done an excellent job of using physics, as simple as possible and no simpler, to help us understand that an attempt to demonize carbon dioxide is not only foolish, it's dangerous. Would you like to add or summarize anything in concluding our conversation?
What bothers me most of all, and it's particularly a problem in the UK, but I suspect it's similar in the US, is what our children are being taught at school. They're being taught. I've been trying to deliver one of my lectures to a school. They keep saying, yes, they'll have me come around one day, but I never get the invitation. And I suspect is that they're actually not allowed to do it, which is odd in the scientific world. Even if you don't want to agree, then please, let's debate it. I'll tell you something else, Angela, which is very interesting. I've had I generally had a very positive response to Tom's presentation. Went down well. When I also lecture to what we call the U3A groups here and in South Africa. And generally, I've had very positive response. There hasn't been one single response that's challenged the physics that I've presented, which is interesting. And I think it tells you something, is that people know that the physics doesn't really support the narrative, but they don't like changing the narrative. Which is a great shame.
Rob, it's been a pleasure talking with you. We look forward to having you again on Climate Debrief. You can find Rob Louw's presentation, The Greenhouse Effect, on our website at co2coalition.org.
Thank you for watching. The Climate Debrief podcast is funded by listeners like you. If you enjoyed listening to this episode of Climate Debrief, please like, comment, and subscribe. We read all of your feedback. If you are interested in finding out more about the CO2 Coalition and its mission, visit our website at co2coalition.org. Our host and executive producer is Angela Wheeler. Production by Ethan Audie and Scott Wheeler. Technical production and editing by Joseph von Spakovsky.